Thanks and welcome everyone. We have more than 50 people attending the economic session, so that's great. Happy to everyone is here. The format, as you've seen, if you have attended other IAMC panel sessions, is the following. We're gonna have 10 minutes talks, following by 5 minutes Q&A. We have 6 speakers lined up for today's talk, for an hour and a half of 1 hour talks and half an hour of Q&A. And so let's just get into it without further delay. We're gonna follow the agenda as in the PDF. And we're gonna start with Johannes EMMERLING from the European Institute on Economics and the Environment, talking us about within-country inequality. Take it away, Johannes.
Yeah. Thank you, Max, and thank you everyone for attending this session. I'm happy to start the discussion on the economic session with the work that we have been doing with several co-authors that you can see here on adding within-country inequality and links to climate change and climate policies in an IAM for now, with an application to France and Brazil. So basically, what we're doing in this work is to try to look at the issue of inequality within countries, which is quite often neglected, especially in large-scale integrated assessment models, which, however, has received, let's say, great attention in recent years. That it's quite relevant both from a policy incidence point of view and also from an impact of climate change point of view. So what we've been doing is we've been doing quite some data collection from several household surveys and labor force surveys, trying to aggregate consumption of different goods or different goods categories by deciles or quintiles. In the end, we ended up doing it with deciles. And we wanted to build a kind of inequality module to include and soft link to the IAM, which can basically endogenize how the income distribution within a country evolves based on the macro framework and some additional data that we add to the model. Now, income inequality is a big topic, and it's a big literature, and nowadays, since Piketty's book has been even more increasing, that and of course we need to model, let's say, the sources of income inequality. So where does it come from? Because we really want to model the evolvement and therefore also the changes and dynamics over time of income inequality. While income inequality comes from several things. I mean, in economics, it's considered one main reason being skill premia. So we have, let's say, different skills or education levels that lead to different labor returns. So skill premia are important. But on the other hand, we have also capital income and capital distribution, wealth distribution, which leads to different capital gains. And so that's another source of heterogeneity. We have savings that are not uniform across quintiles, so saving rates vary. And this, of course, in the long run also determines income distribution. And we have different consumption patterns, different consumption goods, consumption shares. And here, in the focus of in the context of climate change, especially, it's about energy in form of transportation, housing, and also food to a bit. Now, with the sake of time, I have only briefly discussing how we did it. So we went to the households. Here you see a couple of data on quintiles. For instance, for Brazil, we categorize expenditures from household service by, let's say, general expenditure, food, energy, on housing, and transportation. And you see here, for instance, for the 5 quintiles, that basically we see higher shares of these energy-intensive goods for lower quintiles. We also have income distribution, and I will show a bit how this varies across the deciles. So this is basically the all input work that we do, and then we approximate it by quintiles or now deciles, and we see, comparing it to the actual distribution, for instance, the Gini or Lorentz curve, that we match the broad distribution over the whole income levels pretty well, I think. Now the model just, looks a bit like this. So we soft link an integrated assessment model you see here on the left, which is the WICH model, to an inequality module, which has additional sources from household surveys on income, consumption, saving rates, wealth shares, etc. And the model bringing quantities and prices of different sectors. and then basically the inequality module computes the distribution of income, consumption, and all kind of variables across these deciles. This shows you a bit the data that we use. So we produced a kind of template for collecting data, and we are in the process of collecting many more of these harmonized data sets for other countries. So it's quite a lot of data because we want to really capture heterogeneity in households. So we have income shares of different incomes, consumption, as I said, but also savings rate, educational attainment, because this matters for skill premium, wealth shares, and also differential returns on capital, because they are not uniform across quintiles. The inequality module itself is basically a microeconomic model, a simple consumption and optimization model of household intertemporal consumption allocation, and then also allocation across goods, where we have price vectors, which comes from the macro model, so prices of energy, prices of food, and other goods. And then the household basically decides how to allocate its consumption level based on income, based on its wage, and capital returns. So we have labor and capital returns, how to across these goods, and this is optimized for all the deciles in the economy. So far we did an econometric work there. We empirically estimate how income inequality, here focusing on an income because that's the main impact of climate change on inequality, and we estimate here a relationship to the Gini index, and we find that similar to what Burke did on GDP growth, that well also inequality seems to be most optimal, or let's say lowest, at these kind of intermediate temperatures, which are a bit higher than Burke 13 degrees, but in this range, and it's increasing as you turn or colder or hotter. So we inequality. Here you see just the input data, how it looks. Now we started with quintiles. Now we are doing basically decile analysis, and here you see, for instance, how income looks on the top. And as I always comparing these two countries, which are Brazil and France. So we have like a developing or emerging economy and an OECD country on the other side, and we see also some differences. So here we see how labor, capital, and transfers or other benefits from the state depend. Across deciles, so you have a huge share which are basically other goods, all the other goods that we don't consider, and we have energy for housing, transportation, which are the green and blue colors here, and food consumption. Now, food is of course also linked, and it's increasing with the deciles. And this is also something that we can capture, which is actually work ongoing. But yes, we have the three categories: housing, transportation, and food. And you can see that all of those basically increase in relative shares as you get poorer, even though the pattern is much more remarkable in Brazil than in France. But even there you can also see it. Okay, so here we implemented this model, and at the moment, we're running it for different scenarios. And here, just to give you, for the sake of time, a preview of the results on income. So this is basically the result on income inequality. And here we run the 5 SSP scenarios, and we run a carbon budget of around 800 gigaton of CO2. So like a 1.5, 1.7, 2-degree policy, and also a $30 carbon tax. And you see the 5 SSPs and the Gini for income for all countries. Now the baselines here for the projection are based on a paper by Narasimha Rao. And here you see by the different line types basically the impact of introducing a carbon tax. And what you can see is basically that in most scenarios you see an increase in inequality, especially in SSP 1 and 5, which are, let's say, optimistic ones, by about 1 to 2%. If you look at the numbers here, so the scale is as you can see here, meaning that because of this regressivity or of energy and food shares, energy consumption shares, basically it increases inequality. Now for SSP 3 and 4, it's a bit different because they have already very high levels of inequality. As you can see here, Brazil reaching over 0.7 on Gini, which is a very high level. At which point, there's the pattern even you can see some reductions, but this is because there's huge shifts in income inequality that we implement in the model. So, but the main point here is just to say that while you see an impact of carbon pricing because we have this consumption side and this translates into Gini index differences. We then could look also at consumption. So we end up have the consumption share. So these are basically consumption per category. So we have buildings, energy, other, which is basically everything else, and transportation. And here you see that with carbon taxes, which are the dashed lines, you reduce, of course, because of the much higher prices for transportation and for energy, you reduce this consumption, and this one affects poor household to a higher extent. Whereas other goods are basically not affected so far because they are not priced additionally on carbon tax. We also have this income, this impact work, which I just mentioned, but for the sake of time, just to go to the conclusion that maybe just from this last graph saying that, well, we looked only at the mitigation part so far, that is on energy consumption, but on the other hand, what we find empirically is that also impacts increase inequality. As you can see here in the graph across SSPs, the increase is around 3 to 4 percentage points, points on the Gini scale for an RCP 4.5. So basically combining those two will then have combined these two effects. So we have kind of an increase on Gini on the mitigation side. So far, we did not do any recycling scheme experiments. This is a pure uniform carbon tax. On the other hand, inequality will raise because of impacts. And we see also some differences across those two countries. But as I said, so this is a work in progress. So we have a lot of open issues, and also happy to hear any questions and try to answer them. We have food consumption data, so we will also include this in future work because it's also very important. And as I said, integrate impacts. And what we also want to do is to run this module basically based on the last 20 years of data for which we have data, based on past surveys to see how well the model performs in terms of a hindcasting exercise. But with that being said, I think I reached my 10 minutes. So yeah, thanks a lot again, and happy to answer any questions now or in the chat also. Thank you very much.
All right, thanks. Thanks, Johannes, for being in time and presenting this work on inequality. As you see, economists do care about inequality as well, and not just efficiency. We have a question in the chat, in the Q&A, and please use the Q&A for whatever comes to your mind, also as I speak, and I also pick them up as we go, or also if we have some time at the end for session. By the way, I forgot to introduce myself, which is bad. My name is Max TAVONI. I work at the European Institute on Economics and Environment. So, as you see, we have many colleagues in this session, given the focus on our institute on this topic. There's a question of the SSPs, since they obviously derive from what you see shown as they derive results, inequality and Gini coefficients, they are driven very much by SSP assumptions. So can you say more about assumptions about inequality in the SSPs?
Yeah, so the SSPs are very diverse. I mean, this is known that, and they have to be structured and designed in a way to capture very different worlds, right? So it makes sense that and this is kind of not our results, these are kind of estimated relationships based on this paper, but it's also, if you look at the storyline, they are all kind of, let's say, plausible scenarios. Now, the problem we had was kind of to implement them in a kind of microeconomic foundation that determines such inequalities. But we managed to do so because, as I said, we have skill premia, so we have education. Educational attainment is also, I mean, if you look at the graph, it's very different across SSPs. Like SSP 1 has also a very high and very fast improvement in education and kind of really across the board across the world, which then also of course would lead to much lower differences in skill premia. And so we kind of match the SSPs by the underlying assumption of the microeconomic model, and we see that they are kind of consistent, but they are just depending on very different scenarios. But of course, then in terms of what happens to education, this is not what we endogenously model. There we take also the SSP scenarios. Mm-hmm. We just match them in a joint microeconomic framework. Exactly.
Johannes, there's a question about the plots as a function of temperature. Is the curve with respect to temperature different for different income groups? I assume that
Yes.
relates
Yeah.
to the impact tour.
Yeah. Yes, we also ran it for different deciles, and indeed, I mean, we see the strongest effect for the lowest 3 deciles, so that's the poorest 30% in the population. There you see a strong. The shape is always quite similar. It is more significant and more U-shaped for the lower deciles, whereas for the higher deciles it becomes flatter and therefore less significant. But yeah, so it varies, but for the poorest deciles it has the strongest impact. So
there's a two quick questions, and then we're gonna close. There's one question is asking whether the inequality model has been calibrated against the RAO estimates for Gini, and the other is more to what extent the climate feedback affects economy and the different deciles.
Yeah. Yeah, so for the calibration, that's actually what we're working on, to calibrate it, and we basically we calibrate to this more econometric. But find not so many differences. Actually, it's quite surprising. It matches quite well the estimates, but that's the detail. And yeah, finally about the not yet included, but I mean, yeah, we have this impact on the inequality itself, and yeah, we will try to add it on income. Basically, just the effect on income. That's the one we want to capture.
Okay.
Thanks,
Johannes. Thanks for the questions. Great questions. Let's move now to Paolo Gazzotti from Politecnico di Milano is going to talk about inequality again. So the 12 topics are related, but in cost-benefit scenarios, slightly different topic. So take it away, Paolo.
Okay, thank you, Max. I hope you can hear and see well. And okay, again, thank you. And this is Paolo. I'm a PhD student from Politecnico di Milano. And now I'm going to present you some results from our paper called Persistent Inequality in Economically Optimal Climate Policies, which is currently under review. And before starting, just let me take 2 seconds just to publicly express my deep gratitude to all the people who helped and have contributed to this work. And now let's move in. Now another screen. Let me give you a very wide overview of the model and the methods we use, and then we focus more on the results. So we implemented the so-called RISE 50+ model, and as the name is saying, it largely inherits from the Nordhaus Dice RISE specification. So it's a model, a Ramsey type optimal growth model, which optimizes consumptions with a Cobb-Douglas production function, investment savings rate, all for the different independent regions. And we actually have 57 regions. They are shown in this map. And as you can see, there are few macro regions left. We have a pretty fine detail, which is driven by the finest data available. In our case, it's the marginal abatement cost curves. And this model can be run both in cooperative, so a social panel which optimizes the global welfare, and a non-cooperative scenario where everybody is doing a self-interested strategy, which leads to a non-cooperative, so a Nash equilibrium solution. And so these are our main calibration sources, the NRData and Future MAC curves, which are for 57 regions that they define our regional choices. The SSPs baseline projections for both population and GDP. And then we introduced this widely debated empirically estimated impact functions. We mostly focus on the Burke assumption, and which is relating the effects of climate change to GDP growth as a function of the annual average temperature. As you see, it's basically relating the change in GDP, define this U-reverse, U-shaped relationship between the change GDP per capita and annual average temperature. And so in order to do so, we had to introduce a temperature downscaling, which is relating the effect of global mean temperature increase to local temperatures, and this is a regression calibrated on the CME5 dataset. And we also slightly changed the welfare function of the model. We introduced this disentangled version, which basically adds this inequality aversion parameter on top of the elasticity of majority and pure rate of social time preference. And this inequality aversion, the effect is pretty evident from the figure which is shown here. So there are mitigation efforts for several scenarios plotted on against GDP per capita. So you see that non-cooperative scenarios, mitigation efforts are basically left to the poorest countries, whereas on cooperative, it comes the inequality aversion. So you start from inequality from 0, which is a substantial neutrality. And then once you rise this value, you have richest countries which are doing more mitigation in order to try to preserve the poorest countries. And you also see that there's this saturating effect. So you can't go beyond this 2 value because there's no additional effect due to the mitigation limits. And so then we run this model in benefit cost optimization, running a full combination of all these drivers. So we have the SSP baselines. We have 4 alternative specification for Burke impacts, accounting for short or long run for impact or differentiated response from rich and poor countries. And we also implemented other empirical impact functions like DAL and CAM, which are for robustness. We ran both non-cooperative and cooperative scenarios, and under cooperations, we defined 4 levels for this inequality aversion. And we also introduced 3 levels of utility discount rate. So let's say the results. Let's start from aggregated projections, and let's start from world aggregated industrial emissions. As we can observe here with non-cooperative scenarios, we have some substantial mitigation with emissions which are basically flattened, and they differ from the BAU as intended as a no mitigation at all. But they also have a wide range as non-cooperation is strongly driven by the general setting. Whereas for cooperation, which is the green line, we have here we are showing at the intermediate inequality aversion. We have a steep decarbonization with some negative emissions by the end of the century. And the result in global mean temperature increase is that under most of the cooperative scenarios, we are, you can say, to be Paris compliant in an optimal solution, which means we are below the 2 degrees, whereas for non-cooperation and BAU, of course, we are we reach much higher temperatures, close to 3, but that can range up to 4 and beyond. We also have the composed uncertainties, but let's move forward because here we have the mitigation efforts and costs for 2K time sets as they are 2030 and 2050. In 2030, we compare our mitigation effort distribution with the NDCs as estimated by Hofstang, and we both projected the conditional and unconditional NDCs. We know conditional have a slight more ambitious mitigation, but as you can see, they are basically aligned with our non-cooperative outcomes. Exception are Europe, which is from a green transition, which is very ambitious, and India, because in India, Burke function is estimating very, very strong damages. So, of course, the consequences that mitigation effort are pretty high already in 2030. And the general perspective, yeah, you can see the difference between the non-cooperative setting and the cooperative, with both in terms of ranges and ambitions, with the 2050, where main of these macro regions reach carbon neutrality, and also the different mitigation costs as a consequence. That's good to the main point of this presentation, which is inequality in distribution. So let's focus on this panel, where we reported the distribution of this inequality index evaluated as the 90-10 and 80-20 percentile ratios over population-weighted distribution at the end of the century. And this is done for all the scenarios. So we can compare the no climate change scenarios, which are the purple one, distribution, which unsurprisingly are getting higher values for this index, which means worse inequality for non-cooperation. But most interesting, we have also cooperation, so a kind of good option, good scenario, which is improving the situation compared to non-cooperation, but it's still worse than non-climate change scenario. And this is also pretty evident here in the main panel. You have the no climate change reference on top, then non-cooperation with a wide distribution, and most of the population is in the lowest range, and some countries are also gaining because of the impact specification. And then you see that in the cooperation, you shrink distribution, but you are still far from the reference without climate change. And this is also compared to today's level. You see that many scenarios project an improvement, but you also, in cooperative cases, this index can get very worse in some scenarios compared to today. And this is something pretty robust across all our drivers. Let me show the most interesting, which is maybe the SSP. So we have this consistent pattern here. We are showing for all the SSPs. On the top line, we have the index value, pure value distributions. And in the bottom line, we have the index differences as a percentage compared to today level. And what we see is that the pattern is consistent, and took the two extremes, so the SSP1 with the lowest inequality assumption, which is underlined, and we have improvement compared to today, but yet less improvement than a no climate change scenario. Whereas on the SSP4, which is underlying the highest inequality, it gets worse by hundreds of magnitude compared to today level. So what we observe is that basically the pattern is consistent, and the SSP's storyline is exacerbating this pattern. And it's also consistent to inequality aversion, as we can see here. On top line, we have mitigation costs, which are higher for richest countries for highest inequality aversion, but that doesn't change much the story, especially on the side of impacts, because as you can see, they are still highly regressive, and they are very strong. They reach up to -50% because due to the Burke specification, and this pattern is consistent across also the other impact specifications. And so we conclude saying we run this model with 57 regions. We confirm the Pareto, the optimality of Paris targets, and this is most in line with non-cooperative optimization. But we observe this alarming worsening of inequality as income distribution. And this is a consistent and pretty robust pattern, which comes on top of what we already observed in the past. And this is strongly driven by our Burke and other empirical estimation, but it's definitely something that needs for strong investigation and raises important questions, like time left for useful action. And thank you for the kind attention.
Thanks, Paolo, for your presentation. Attendees, feel free to ask questions in the chat. There's a question asking you, saying that essentially you compare the inequality in cooperation, and you say it's higher than in the BAU without climate impacts. But how does cooperation compare to BAU with climate impacts?
Well, compared to BAU with climate impacts, of course, we didn't check that in terms of inequality, but as we observed by the general framing, we are pretty confident that it's improving the situation. So the BAU with climate impacts is definitely the worst case, which is kind of unrealistic, because it's really like everybody is ignoring those strong, super strong impacts that are projected. So it's quite difficult to defend the BIU with the impact scenario. It's just something we put for reference in the general case, but it's most, I mean, the true baseline here maybe is the ranges inside the non-cooperation case. So I would keep those as the most relevant reference.
Thanks, Paolo, and
thank you.
Let's now move to our next speaker. We have Jia Li, I hope
yes,
from the US EPA, talking about climate justice and mixed methods.
All right.
Floor is yours. Okay.
Great. All right. So good morning, everyone. My name is Jia Li. I work at US EPA in the climate economics group. So I'm presenting some work, which is actually a new project we're starting in collaboration with my colleagues at the climate economics group, and also John O'Neill from University of Maryland. So I want to acknowledge all the collaborators. So let's see. Can you see the screen? I couldn't see very well what's projecting on the screen now. You can see the motivation.
Yeah, that's perfect. We can see.
Okay. So from different social science disciplines, it has been discussed in the past in the literature. This is long known that social inequality is both a driver of climate change and also a major factor that contribute to differential vulnerability of a different population. So the environmental pollution exposure, climate change impacts and risks are distributed unevenly, with low-income minority communities and marginalized groups sharing more burden. Both, the evidence was both clear in the U.S. and also in other countries. So in 2020 in the U.S., I think everyone would know, because of the pandemic and also this social justice movement in the U.S. is putting new light on just looking at the disproportional impact of some of the social economic policies and also environmental pollution on EJ communities. And increasingly there is more interest and also a call for reflection of environmental justice consideration in climate and environmental proposals, policy proposals. And there's definitely a need to really have better enhanced data and analytical capabilities to study the distributional implications of climate policy for different social demographic and groups, and also in different regions. So that's the motivation for our work. So briefly looking back in the economic literature, so in the climate policy analysis, at least in the economic literature, distribution impacts has been studied quite extensively, both looking at the mitigation policy and also looking at adaptation responses. Many of these are using economic models, including IAMs, for analysis. I cited a few just on the studies in the US, looking at various policy designs and their implications for different income groups and different regions, and to some extent, demographic groups as well. But oftentimes the studies currently, as they are in the literature, are limited in the spatial and social demographic disaggregation to really understand, like the question related to racial justice. It's partially a reflection of data collection limitations. So a lot of the socioeconomic data are not collected at the scale and resolution that we would like to see. And the other, I think, reason is the representation of consumers or households in economic models, as we know, oftentimes is quite aggregate. And the other part that we found out through our own review is also that if you solely look at income as a metric, sometimes we could overlook consumer heterogeneity that, in the welfare analysis, that ideally we should also be looking at other household characteristics and perhaps housing, geographic, and institutional attributes. So we asked 2 research questions in this endeavor. The first one is, how do we define energy burden? What is the pattern of energy burden by income, race, and geography in the US? And what are the determinants of energy burden? And the second one, the ultimate interest for us is really trying to link up some of the microdata and evidence with the economic models we have, CGE and IAMs, to better evaluate distributional impacts of climate policy for different social demographic and groups. So the study approach we use is a few folds. So we started by looking at some of the existing data and tools out there. And we would like to develop a nationally consistent data sets at fine scale, which includes the social economic characteristics, demographic, and other consumption characteristics of the US household. This really has the, the goal of looking at not just climate mitigation policy, but potentially better understand other pollution problems and also look at climate impacts and vulnerability. So we also really spent a lot of time, like the first presenter, Dr. EMMERLING, looking at microdata. So this is what exercise we're going through as well, is really trying to look at the microdata of households to better harness some of the characteristics in the data to describe social vulnerability, energy burden, pollution burden. And we're trying to build this information at fine scale at the local level. And another step we are taking is looking at using the microdata to perform econometric analysis to better estimate consumer demand elasticity, and looking at the relationship between energy expenditure with other social demographic and housing characteristics for different social demographic and racial groups. If I go to the next one, I hope everyone can see, I'm seeing this a little bit differently on my screen. So the first question on the metrics for energy equity. So what we found is very typically energy burden is defined as a percentage of your household income spent on energy. And in the US, oftentimes we use 6% as a benchmark to look at, if it's higher than 6%, it's considered to be higher energy burden for the households. But this varies. 10% is often used by other OECD countries. There are different ways to define that. And this is what we found is that this definition actually requires more investigation because how you define the energy expenditure could matter. Do we include some of the categories like transportation or other utilities could make a difference in housing? And also, how do you define the income also matters too. Do you consider the tax or some payment transfer, which will have implications for climate policy? So the next few slides will just show very quickly some of the data we're looking at. So there's a lot of micro data being collected by the federal agencies to look at household, social economic conditions, demographic characteristics, and also energy and other household consumption. So none of this data sets will give us all the variables and the spatial resolution we might be interested. So we're looking across different data sets and also combining them to really get a better picture of the household consumption pattern, and particularly on the energy side, probably more details. And also there are data sets that actually already draw from the various sources to develop very fine resolution characteristics like some of the social economic characteristic for communities, and also energy consumption, energy burden at fine scale. So we are also utilizing some of these existing tools to build on for our analysis. And the next few slides, I'm just showing a few examples of the data we're looking at. So this one is coming from the annual consumer expenditure survey from the labor statistics. And these data are aggregate. So what we're looking at here is really just separating out different racial groups. So if you look at the income distribution, there are different bars. Maybe it's a little bit hard to see. So income distribution, income after taxes, and disposable income, and annual expenditure. And some of the expenditure categories we're interested in, including housing, transportation, and home energy. So just broadly, you can see like this variation in income and expenditure across different racial groups. So we would like to further disaggregate by including other groups like Hispanic. And if you look at the distribution, you can see more variation on the income expenditure side, the overall expenditure side, than perhaps energy, energy expenditure. So this would also, have implications on how we think about the climate policy, energy policy. So either you give a lump sum payment transfer, or have other economic policy which will increase income or jobs, would probably have different implications on whether the policy would increase energy prices. So this one is a just looking at the various energy burden metrics, by different racial groups. As you can see, it's very clear. Some of the racial groups, particularly African Americans, have a higher burden of both housing expenditure as percentage of income, and also for energy use. So based on the different metrics. And if we look at the energy burden metrics, it also varies, depends on how you define the expenditure and also what incomes you account for. So these are the things that we're looking at. We want to do more investigation. And the other part interesting is really this energy burden also varies quite a bit by geographic location too. So this is a map showing, energy burden by state. It's very coarse, and we have data looking at the county level as well. Probably you will see very different pattern of distribution. So the level of data granularity, the resolution would also matter too. This one is a map showing the kind of the continuum of a county level rural urban designation, just geographically. And if we pair that with some consumption data by differentiating between urban and rural, again, here we see, this is consistent with other studies as well, that you see higher energy burden in the rural regions, but the urban residents have higher housing burden. So all these are pointing, to us is really, we need to look at the various consumption patterns and the different categories to really understand what are the implications from energy consumption. So the next is just a slide showing.
Just to say that we are over already. Just so you can
I'm sorry. Okay, thank you. Okay. All right, so this one, just very briefly, this is county level mapping, looking at social vulnerability, some of the data layers we want to utilize. So we want to do additional analysis using the microdata, looking at various data sets and further differentiating social groups. And the other big component is really economic estimation. So here, building on the literature, we want to add some additional variables, looking at race and also community characteristics to get at some of the institutional, perhaps other socioeconomic underlying conditions. So the second part we are doing, this is still work in progress, so I'll just go very quickly, that we're investigating is the various approaches for disaggregating economic model outputs to look at the distributional impact. So there are different ways to do it. Some of these are probably more suitable for our case, given the data we have and the model tools that we're using now. So we need to have further analysis in the investigation. And this is just showing some of the future work we hope to undertake. Thank you. Sorry that's running a little out of time.
That's fine. Thanks, thanks, Gia. I think it's very important, especially the vulnerability part. It's not just income, but you have rightly highlighted a variety of characteristics which play a significant role. Given the time is up for your slot, I would suggest we move to the next talk so that we keep time right. And I would like to call on Shinichiro Fujimori from University of Kyoto, talking about poverty and how carbon tax revenues recycling can be used to reduce to deal with that. Shinichiro, yeah, take it away.
Can you hear me? All right. So thank you for your introduction. I'm going to talk about an assessment, comparative assessment of carbon tax revenue and poverty gap. So let me remind you the very basic poverty background. So currently we have around 700 million people who are under extreme poverty, which is defined as 1.9 per day per person, counted as a PPP. And as you know, SDG 1 clearly states its goal to end the poverty. But actually, when it comes to the indicator target, it says to achieve the target of less than 3% of the world living in extreme poverty by 2030. So it's not completely eradicate the poverty, but anyway, we need to transform the society to reduce the poverty. And in the meantime, we have a carbon pricing or carbon tax policy to mitigate the emissions. And I guess almost all of you know that carbon pricing and carbon tax would be a quite efficient measure to reduce the emissions. And so far, we have many studies that discuss about how to recycle the carbon tax and its consequences. But as far as I understood, poverty, there is no explicit poverty implications based on the carbon tax revenue, and which has a quite interesting topic, whether it can be covered by only domestic usages, or it can be also used for international transfers. And so my study has these objectives. So firstly, we want to see poverty scenarios. Actually, there are no explicit poverty scenarios right now. And so we started from developing this one. And then the next is we carried out comparative assessment of potential carbon tax revenue and poverty gap. I will talk about what is poverty gap next. And finally, domestic and international usage would be the very interesting angle of this discussions. And as a methodology, we developed a new module in our AIM framework coupled with CZE model. It's called AIM-5, the Poverty Household and Income Model. I'll talk about this model in detail later, but we used 4 main scenarios: baseline, NDC, 2 and 1.5 degree targets. And then the focused indicators are mainly 3, as shown here. One is extreme poverty population. Assuming that this is the income distribution, then we can easily calculate if we set the threshold of the poverty, which is usually $1.9 per person per day. And then we sum up the population here. This is the poverty population, and then we can again easily calculate the poverty ratio divided by population. And finally, the poverty gap is a calculating the deficit of the monetary amount for each segment here. And then we would be able to estimate how much money is needed actually to eradicate the poverty. And this is the flow chart of the information which we carried out the scenario analysis. We started from population, GDP, and climate policy in this usual integrated assessment model. And then we get household income loss and price changes, which is macro level. And then we feed the Gini coefficients and these macroeconomic indicators. And finally, we got poverty indicator, which eventually be compared with carbon tax revenue. And so what is this phi? And in CZ model, we have 17 regions, but we downscale further in individual country levels, which consists of 2 modules, income and expenditure. So income considers the income distribution within countries where we assume a log normal distribution. And then after deciding the income, we pass them into the expenditure model, where we assume AIDS expenditure function. If you are familiar with the CZ modeling, you might have already heard about this term, which is a sort of extension of LES or CD function. And individual segment consumption every $10 for poor is computed, and we have 12 household consumption categories. So we have this income distribution, and we have consumption varieties across the income segments. And this is the results. We start from the so-called baseline population, GDP, Gini coefficients. They are input of this study, and so we took from SSP database, and this is from Narashima's work. And then we get a global income distribution. We basically have a better shift from now to the future. The peak is shifting towards right-hand side, and the level goes down. And then we can get a poverty head count, poverty rate, and a poverty gap, which consistently show the declining trend thanks to the income growth. And when it comes to the country-wise poverty, interestingly, India, Nigeria, the highlighted countries in terms of absolute poverty populations. But when it comes to extreme poverty ratio, the ratio is quite high in African countries like Somalia, Central Africa, and Madagascar, which may be minor countries for many of us, but they are least countries where really needs the help to eradicate the poverty. Then moving on to the mitigation scenarios, we have emissions, carbon prices, and carbon tax revenue, and GDP losses. They further fit into the AIM-5 model. Then we can translate this information into the poverty-related indicators. We have some implications of mitigation scenarios, but we skip this part. I forgot to mention this is the price changes from the CZ model. Individual 12 categories consumption goods have individual responses to the carbon tax policies. And then finally, this is our main goal. So we have carbon tax and poverty gap, and we divided it by GDP to compare these two. And so carbon tax per GDP, it's we can say, it's evenly distributed among countries, because, in this scenario, we assume global uniform carbon prices, and thus the results can be easily imagined. On the other hand, poverty gap is quite dispersed. African countries are mostly located as a poverty gap highlighted. And then we can take the difference between these two. In African countries, like I mentioned, Madagascar, Somalia, and Central Africa, they still show the big deficit in poverty gap. If we want to fill the gap by only carbon tax domestically. And when it comes to the absolute amount of these poverty gap and carbon tax, basically, we have a huge amount of surplus of the carbon tax if we sum up all global total, while poverty gap is very small, which concentrated on African countries. And the country-wise distributions are shown here, but let me skip. Again, the same can be said Somalia, Central Africa, and like such countries have a deficit. And while China, United States, they have a huge surplus, and it can be used. Very small portion can help the very poor countries. And so the implication is that carbon tax revenue has a great potential to help eradicate poverty. And I think international cooperation is essential to filling the poverty gap. And just, less than 1/10 of the carbon tax revenue collected in a large country can easily fill this gap. So this is the conclusion. We explore the poverty scenarios, and we compare with the carbon tax revenue. To do this, we developed a new household assessment model, which is called AIM5, which is coupled with AIM-CCE. And carbon tax is much larger than poverty gap. And thinking about this usage, international cooperation or transfer from high-income countries to developing countries is quite attractive option. But we admit that poverty is not such a simple issue. So it just transferring money doesn't solve. But I would like to burn this kind of argument in the society. Thank you very much. This is already published in ERL, so if you have an interest, please go to this website.
Thank you, Shinichiro. Again, inequality is faring very high in our presentations today. If you have questions, we have 3 minutes for questions, so you can please use the Q&A. Meanwhile, I was thinking, the log normality assumption and the use of Gini, as opposed to using microdata such as those coming from POVCalNet and other similar sources from the World Bank. Do you think is it okay? Is it a good statistical approximation for poverty? Because poverty is a very small part of the distribution. It's a very concentrated tail. In some countries, of course, unfortunately, it is a much larger part of that tail, and for those countries, it might work well, maybe so. But typically, log normal distribution tend to fail to get these fat tails, and that's why other kind of distribution have been used in the past. Of course, they are very useful because they are very tractable. Log normal.
Well, very good point. We also doubted about that, and but we started from POVCalNet, World Bank data, and Gini coefficients, and which can reproduce the current World Bank estimates of the poverty headcount, and thus we used this one. But of course, it doesn't reflect all of the micro or data, and thus if we could improve that part by using original micro data, then yeah, this study would go beyond the current situation. But my understanding that current international recognition of the poverty is basically based on the log normal distribution.
Any questions? I don't see questions. I have a few. So maybe last question from me.
Yes, please.
So do you have the feedback of the mitigation cost impacts on inequality as well in the model, and how is this affecting especially the very poor? In some cases, the very poor, for the very poor, energy is subsidized, and so they should be sheltered from energy price increase, but that's not always the case, of course.
Exactly. That's also a very, very important point. We didn't put any assumptions on subsidies and setting the carbon pricing and so on. So we simply put the every price changes and taxes, and then the consequences is regressive. Basically, poverty increases by these mitigations. Like here, you see, like 80 or 70 million will increase by 1.5 degree mitigation scenarios.
Okay, then thanks. I invite everyone to keep working on Q&As and chat if you have specific questions for Shinichiro.
Thank you very much.
Very interesting, thank you. So let's move to our next speaker. Yeong Jae is also a colleague. Sounds a bit of a family today, not by coincidence. And Yeong Jae is going to talk about spillover, technological spillovers. So we're switching gears a bit, always an economic related topic, but not a bit away from the inequality.
Thank you. My name is Yeong Jae Kim, and this is a collaborative work with Elena Felodili at the same institution, and I'm very glad, and this is my first time to attend the IAMC. I'm very happy to present this research. So why do we care about the technical change in the IAM community? And as you know, the technological innovation is very crucial, very important in dealing with climate change issues. And innovation, promotes a competitiveness of firms and nations and create jobs, and it increased the access to the lot of services to the people. So traditionally, economists delve into this issue and study the drivers and the impact of the technical change in low carbon technologies. And this is pretty much well-established area in the literature. So having said that, among a lot of puzzles in this literature, so we cherry pick three very, very important key literatures in this domain. So first, one literature found that international spillover effect. The second paper that found the inter-sectoral technological spillover effect in low carbon technological area. And third one argues inter-temporal ones in European countries in energy technological area as well. So in this paper, in this research, we want to put the three bit by bits together and combine it and contribute to the WICH model. And hopefully in the future, we can, contribute to IAM community as well. So currently in WICH model is pretty well known for the, good representation of the endogenous technical change. And first of all, it represents the pace and direction of the technological change using R&D database and the patent database. And at the same time, it also includes a lot of very good representation of international spillover of knowledge across different countries, different regions in the model. So in order to tackle and combine these three key ideas in the literature, important pieces, we rely on patent data again, in European patent database, and we divided in different types of technological field. And in this slide, I show you in 10 technological field, and in the later estimations, we narrow it down to 6 important ones later. So we also include 32 countries, including developing ones. And the span time period is 1990 to 2011. We are working on expanding this period as well. And we include a couple of control variables is now an econometric model, like interpreted as barriers of knowledge flows. For example, if the two countries are different, that's the barrier of knowledge. And if two countries are located far away, that's also interpreted as barriers of knowledge. And trade zones and language speak the same language, and whether two countries are, have a similar portfolio of technologies, and whether the two countries are away from the frontier of the technology or located nearby the frontiers of technologies, and similar portfolio of environmental policy stringency distance. So in our paper, we construct the econometric model followed by a well-established method in Paris 2005. That's basically, we rely on a lot of knowledge in the international trade literature. So think of it as a bilateral relationship. So there are 3 steps we approach tackle these problems. The first step is we model the probability of knowledge flows between 2 countries in specific time t and time t0. And second step is we plug back estimated these coefficients into the model, econometric model, and calculate bilateral diffusion parameters. And then third step, which is ongoing, and there are a couple of challenges and open-ended questions that we need to tackle. And maybe if you have ideas, and I would love to hear your opinions and feedbacks later. So I will demonstrate a couple of descriptive statistics. This graph map shows a number of patterns across by different countries, and think of it as Global Innovation Index published by the WIPO. The United States ranked the #1 in innovative countries, and Germany, and followed by the Switzerland, and etc. 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 And these 2 figures demonstrate a very heterogeneous characteristic of different technologies. And the left figure indicates the number of patterns over time. And the red one in the left panel indicates the solar panel. So, a lot of patterns found by the solar panel technologies. And second, the right side of the panel indicates number of citations. So whether this technology cites another technology in different countries, and etc. So as you can see, 2 graphs are very distinct to different. So with this, I'm not going to go over technical detail of the models and equations and etc. But I want to demonstrate the findings, key findings in our result. As I explained earlier about all these control variables can be interpreted as knowledge flow barriers of knowledge flow, and the minus, negative, and significant coefficients are what we expected, because that blocks knowledge flow between different countries. So after estimating that coefficient in the previous table, we plug that coefficient into the above equation, and then compute the phi ij. Ij means different countries, bilateral countries. So that knowledge flow from the top right to the left bottom. So Italy to Korea, Korea to Italy. So let me demonstrate our finding with a nice heat maps. So first, we would like to demonstrate inter-temporal knowledge spillover effect, which can be represented in this way, or many different ways, but we divide it in 2 different periods, before 2000 and after 2001, because Kyoto Protocol was implemented in 1997, and EUET was implemented in 2005 in European countries. So that's kind of rough division between 2 periods. So as you can see, the greener shell tells us that more knowledge flows coming from across different countries. So as you can see, right side tells us that the inter-temporal, the knowledge spillover effect increases over time. So second, a way to tell us the look at this heat map is to divide by different types of groups of technologies, and we was divided by two different categories: renewables and non-renewables. As you can see, the renewables has more green cells, which means more active knowledge interactions flows across different countries. But on the other hand, non-renewables like quite a is small, relatively small amount of interactions across countries. So also we can take a look at the distinct technological field, and wind and solar, and wind a lot of more interactions than solar, and we can do a lot of many things. But just this demonstrative purpose, I just want to give you some hints and ideas. So let me conclude. And first, we confirm it's not surprising result that countries rely significantly on knowledge production of foreign countries to produce low carbon technologies. Remember the dark green cells, but also the distinct patterns of the countries. But we are not really actually dig into or examine the cross technological spillover effect with this setting. So this is another thing we are working on. But there are some technical challenges because the dimension of the 32 countries, 30 times 32 countries, and 10 number of technology and 10 number of countries, and etc. increases the number of dimensions. So that's the one thing that we are working on. Open-ended question though. And third, we confirm that a knowledge diffusion increases, over time. It's not constant over time. So future work. So we are currently working on calibrating and there's technical change dynamics in rich model. And based on these findings, and we are trying to update consolidate 3 pieces of the important information in the rich model. And at the end of the day, what we want to aim to achieve is to improve the modeling of the innovation in entire, at least the bottom up, of course, the IAM communities. Thank you. And any questions and feedbacks are more than welcome.
Thank you, Yeong. Very, very interesting talk, very relevant also on different topic. Please enter your questions in the Q&A. It's a bit tricky because if people likes questions and the question move in the orders of the questions. So
yeah, I'm trying to catch up with that. Yeah, I
escape up now. I can do the intermediate here between the questions and you. I had just one question on the charts that you showed. Those are not symmetric, right? So the matrices, the heat maps were showing. I was naively assuming a kind of relatively symmetric flows, but they are not. So there's a symmetry in flows of knowledge between countries. I thought that was.
Yes, you are right. That's not symmetric because mainly because of the environmental policy distance variables, they create asymmetric between countries. That's the major barrier because country distance variables definitely symmetric, right? Because distance between one country to the other country and one country is definitely the same. So it creates the symmetric metrics, but the environmental policy distance to different countries create a, it's gonna be like inverse. Think of the inverse, like A over B or B over A creates different things. So that creates a asymmetry in our analysis. Yeah. Any other questions? Yeah. I cannot see it. Yeah.
Did you look at specific countries? Asian countries, for example. China has grown a lot in terms of knowledge capacity and patenting capacity, and also did you do some deep dives on the very large innovative countries to see to what extent environmental policies elsewhere, for example in Europe, have been playing out?
Yes, I agree. That's excellent, good point. Yeah, but unfortunately, we haven't really delved into that area as well, and due to the current setting of the limited period of time until 2011. Yes, but that's gonna be the next step that we are working on. Yeah, we should definitely delve into that area. Yeah. Thank you, TAVONI. Yeah.
Okay, thanks. Thanks, Yeong. I think time is up, and now it's time for our last presentation, last not least. I would invite Alex Koberle from Imperial College to come online, and Alex is going to talk about financial risks. Another relevant, clearly relevant topic.
Let's put a laser pointer here. Okay, and you can hear me okay?
Yes. Okay.
So thanks for the opportunity to speak about this study that we've been conducting here at Imperial College. With this is ongoing work that I'm doing with these colleagues at the Center for Climate Finance and Investment at the Business School. I'm based at the Grantham Institute, and I have 50% of my time at CCFI. This is part of a long-term research agenda, so I'll try to put this in the context of that a little bit as well. This study is about estimating financial risks from an energy transition to the European power sector. The long-term research goal that we're trying to come to terms with, that we're trying to explore, is filling this gap between the outputs from IAMs, scenarios, transition scenarios, into the modeling framework of financial risk and opportunity also, which happens at the level of economic agents. So, you know, there's a scale difference here, so we need to downscale down to the level of the operating changes for economic agents. And in order to do that, we need to bridge this particular gap. So for going from IAMs, energy systems models, land use change models, into financial variables like cash flow, EBITDA, probabilities of default, we need to do scenario expansion, and this usually involves additional tools, models, assumptions, data. And what I'm going to show here is one example. We've used other approaches as well, but this is one particular example on how to do that. A lot of these tools that are coming up, there's several that are being put out recently in the last few years, have been assessed by an ETH study that came out a few months ago, and they assessed 16 of them. So for this study, we have what we wanted to do was to try to understand transition risks to the 29 largest European utilities, and to assess the capability of these firms to navigate a low carbon transition that is projected by an IAM in order to be able to make the necessary investments, to meet their liabilities and stay solvent, and to also produce a return on investment. So we started with an existing scenario that was produced by JRC GEMI3 polls framework, and is publicly available data published in the GECO 2018. And this was used as input for a corporate model that did the firm level assessment. There are several additional assumptions that need to be taken in order to enable this linkage. So we use basically three outputs from the IAM: the capacity, the generation, and the cost of electricity produced by technology type. So the cost was basically, we just use the LCOE that came out of the model. The total capacity and generation mix from the IAMs is then set as a target for the firms to attain. And because we're only using 29 of the largest power utilities, they're not all of them. So we had to scale the total capacity that is deployed by the IAM down to the current install capacity of these 29 firms. And then we just wanted to assess to what extent they can keep their market share. So to keep that share of the installed capacity. So firms deploy new capacity based on their ability to fund them. They're not forced to invest. They're not forced to meet that target. They do it if they can. The ability is constrained by the firm's own capital structure and their debt covenant requirements, how much debt they can carry. And so this basically results in a financial feasibility test of an expected climate policy outcome for this sector, the climate policy being transitioned to 2 or 1.5 degree consistent with global attainment of that. So this is our framework. So we have the IAM here, which you know what that means. And then we have the corporate model there's an assumption on electricity prices, and then that produces some of these outputs. These are financial relevant outputs. The assumptions that are made, I'm going to get into the assumptions for the corporate model in the next slide, but I just want to mention that the electricity price is here on this study is set to maintain observed price margins, basically cost plus, so LCOE plus a fixed margin. We needed additional company data, and this is the kind of data we got from Bloomberg. And just so you know, in the future, we are also including an electricity price model that another colleague developed here at Imperial. So the corporate model, it's a modified Merton KMV model, and it's standard credit risk modeling financial analysis. There's nothing new in using this. It basically allows for a time-dependent adjustment of asset returns and divides the long and short-term liabilities. So a firm must be able to pay for the liabilities that come due within 1 year, not for their whole debt. The additional assumptions that we make within this corporate model is that there's a fixed debt to earnings ratio. There's no new equity raised. The model allows for this to be relaxed, but for this study we kept that fixed, so they cannot raise equity. The dividends are fixed. We also ran a no dividend sensitivity. Firms will have to spend their cash before increasing or repaying debt. Firms can only invest in technology they already have in their portfolio. This is a pretty hard assumption, but if a firm has absolutely no wind, for example, in their base year portfolio, it's assumed that they will not go into that technology in the future. Of course, this can also be relaxed, but we wanted to test what an extreme scenario would look like. Like I said, the electricity price follows this cost plus with a fixed margin. And then we did planning horizon sensitivity. So we allow the model to look forward into the capacity deployment from the IAM, either 5 or 10 years, to see what that may entail. And like I said, the total capacity scaled just to the capacity of the 29 firms. So going into some results, I'm showing here is the capacity build out by the 29 firms across scenarios as a function of electricity price assumptions. So we go low, medium, and high electricity prices. And as we see, as we go from the reference to the 2 degrees fixed dividends and no dividends, the colored areas move up, meaning that they can deploy more capacity if the electricity prices are higher, meaning that they have more money to invest. So their returns are better. The dotted line here is just the scaled down capacity deployment by poles, by the IAM, right? So although what we see is that the low prices basically mean that there's a gap here. So the firms are losing market share. They're not keeping up with their share of deploy capacity. The higher prices allow them to gain a little more in the long term, but there's definitely a short-term difficulty. There's challenges in the short term. And not paying dividends, so stop paying dividends and reinvesting that money instead actually helps them, their investment capability. So now if we look at equity returns for a reference scenario using a 10-year planning horizon, we divided the firms into 2 types, those that have more than 75% of their electricity generated from fossil fuels and those that have less than 25%. And in the reference scenario, the scales are not the same here, so sorry about that. But they're both cumulative equity returns are about 100%. And because they're cumulative, these flat lines mean that there's a bit of stagnation on returns for the median, although there's quite some variation across the firms, and the error bars get a little larger for the fossil firms rather than for the renewables. If we then look at the 2 degree scenarios, not much change for the fossil firms, but the green firms start to have better returns. So as we would intuitively expect, as we transition, there's more demand for renewable energy, there's more economic gains for those firms that move along that transition path. Now, both of these results that I just showed, both the reference and the 2 degrees, are for 10-year planning horizons. If we then shorten that to 5, we get a very large difference. And we start seeing many firms that are fossil, they cannot make that transition, and there are a few firms that actually fail. I mean, you know, at this point, this firm is not solvent anymore. And also, the median begins to drop, meaning that after 2035 or so, there starts to be generalized losses across these types of firms, while the situation for the renewables heavy firms is a bit less optimistic than in the 10-year planning horizon, but they remain solvent and they continue to produce positive returns, although a few of them may fail in the long term. So just in terms of conclusions, what we're finding here, and actually a big finding from this is that it's a strong argument for a clear policy path, right? So if firms have a clear view of what is coming, not just what the transition is supposed to achieve in terms of emissions reductions, but how that is distributed across different technologies, which technologies are going to gain share, then they can make the necessary investments. It makes it a lot easier. It also shows that the planning horizon assumptions actually do matter, as all assumptions will matter in a situation like this. The model can be quite sensitive to a few important assumptions like electricity prices and planning horizon. So there's just a broad conclusions here. The firms with higher shares of renewables tend to perform better financially, but fossil heavy firms can not only survive, but also yield returns. Some of these firms actually they navigate the transition quite well. And a lot of this depends on their starting point situation, their base year situation. If they're heavily leveraged already, they will have a harder time making that transition. So existing conditions, just like COVID, really matters. And by the way, this study was done before COVID, so we did not include some you know, the scenarios that we use here were not COVID relevant. But the 29 firms, they do lose market share, so it's either a risk of capacity shortfall or an opportunity for new entrants or some of the other firms that are already in the market but have a smaller share. Assumptions matter. High electricity prices close the capacity gap. Of course, that has implications downstream, economic implications downstream. So it may just be that the level of electricity price increase may be too high to even make the transition feasible. So there will be that would exacerbate the problems of those firms already having difficulty in transitioning. And not paying dividends may be a strategy to help improve the capability for the investments required. And the planning horizon, again, is a great argument for a clear policy path. We did not model the equity change, but the model could also explore that, and most likely from some tests that we've done, raising equity would help the transition. So that's what I have, and I'm happy to take questions.
Thanks, Alex. Alex, great presentation. Very important scenario expansion, as you described. There's a question on ETS. I assume these firms are regulated under the ETS, or most of them. To what extent do we account for that? I mean, to what extent companies already account for that in their investments?
Well, they are already accounting for that. So there is already a transition taking place, but because we are looking at just financial variables that are coming from the Bloomberg database, and we're taking the transition as an exogenous input from the IAM, it's just the capability of these firms to make the necessary investments to align themselves with this transition path as described by the IAM. So we're not explicitly modeling the ETS, although the constraints of the ETS would probably play into how the burden is shared amongst them. But this is just looking at firm level capability. It's a firm level financial risk model.
And I guess besides leverage, a key factor must be related to how old the capital stock of the firms is in terms of.
Yes, yeah, we also model that. So
right,
data. So
Yeah, so I mean, fossil fuel companies whoever have plants who are very old and they're about to renew their investments might be better placed than others who made just investment just 10 years ago in natural gas power plants.
Yep. Yeah, some of that may be already captured in polls. I would suspect that they have tracked vintaging from the existing capacity. Although, yes, when we come down to allocating that across the firms, then yeah, it definitely matters. If a firm has a lot of brand new, non-amortized assets that they would need, then they'll probably suffer a bit in retiring them.
What kind of risk preferences do the firms make these decisions under? That's the question.
What kind of risk preferences?
Correct.
I'm not sure I understand what you mean by risk preferences. They just try to meet their liability. So the Merton model, it takes assets minus liabilities, and it has to stay above zero, right? So it's just taking the present value of all the assets, including future revenues, cash flows, and comparing that to future liabilities and the debt structure, taking into account the debt structure. So that has to stay above zero. And the risk preference, because they will compare what they see coming, the changes that they see coming from the IAM scenario to the planning horizon that we allow, and try to match that to the best of their ability. If they have cash in hand, they'll make the necessary investments to maximize their returns. I don't know if that answers the question, but.
Okay. So you have data at the firm level, right? So did you check whether there's any equity? I mean, some of the firms who might be in trouble have already lost in equity value over the past years. If not, you can tell us where not to put our money then.
Yeah. well, this is finance. So the equity, what we're meaning by equity here, the asset value is the book value, right? It's not the market value. So you can have firms that, for if you look at across the spectrum, if you look at Tesla, for example, like the valuation of Tesla does not necessarily reflect the cash flow that it has. So there's a market to book ratio that brings in completely different dynamics, which is more like behavior in the financial sector, etc. But yes, there are firms that since we used the base year was 2018, and this scenario was also run in 2018 for the IAM. So most of this paper has been under review for a year and a half. So it's the scenarios that we ran a while ago that so much has changed. I mean, just talking about this stuff before and after COVID will make a huge impact.
Thanks, big thank to all the 6 speakers and all the attendees.